Hello everyone, welcome back to our course series on Python for data science. In this video we will discuss about Pandas DataFrame. To be more specific, we will be looking at how to create a copy of original data. We will also be looking at how to get the attributes of data and how to index and select data. So, let's dive into Pandas and its powerful data structure called DataFrame. Pandas is an open-source Python library that provides high-performance data manipulation and analysis tools. It's considered one of the most powerful data structures available due to its performance and data manipulation techniques. The name Pandas is derived from the term panel data, which is an econometrics term for multidimensional data. So, Pandas is designed to handle multidimensional data efficiently. Now, let's talk about the data frame. A data frame is a two-dimensional size, mutable data structure that consists of rows and columns. It's basically a collection of data arranged in a tabular fashion, where each row represents a sample or a record, and each column represents a variable or a property associated with each sample. For example, in the data we will be looking today, each row represents a different car, and each column represents a different attribute or variable of that car, such as price, age, km, fuel type, HP, met color, automatic, CC, doors, and weight. One of the key features of a data frame is that it can contain heterogeneous tabular data, meaning that each column can have a different data type. When you read data into Pandas, it automatically assigns a data type to each column based on the data it contains. You don't need to explicitly specify the data type for each variable, which is quite convenient. Another important aspect of a data frame is that it has labeled axes. This means that each row and column have a label or a name associated with it. The row labels are called the index, which starts from 0 to n-1, where n is the number of rows. The column labels are simply the names of the variables or columns. For instance, in the provided data, the row labels are the numeric indices, 0, 1, 2, 3, and so on, and the column labels are the variable names like price, age, km, and so forth. So, when we say labeled axes, we're referring to these row and column labels or names. It makes it easier to identify and work with the data in a more intuitive way. So let us start by importing necessary libraries. First we import Pandas library using import pandas as PD. We assign an alias PD to refer to the Pandas library. This is a common practice to make the code more concise and readable. We also import the numpy library as NP to perform numerical operations if needed. To import a CSV file, we use the read_CSV function from the Pandas library. Since we have assigned the alias PD to Pandas, we use pd.read_CSV. Inside the read_CSV function, we provide the filename, with the .csv extension, as an argument, enclosed in single or double quotes. We assign the imported data to a variable called df. This variable now represents a Pandas data frame containing the data from the CSV file. And here are few observations from it. When you import a CSV file into a Pandas data frame using pd.read_CSV, the first column in the data frame is automatically assigned a row index like 0, 1, 2. In your data, there's an additional column named unnamed 0. This column seems to be serving the purpose of row labels, which is redundant since Pandas already assigns a row index by default. The remaining columns represent different features or attributes of the cars in the dataset. Let's go through them one by one. Price, the price of the pre-owned car. Age, the age of the car represented in months. km, the number of kilometers the car has traveled. Fuel type, the fuel type of the car. HP, the horsepower of the car. Met color, a binary column indicating whether the car has a metallic color. Automatic, a binary column indicating whether the car has an automatic gearbox or manual. CC, the engine displacement or cubic capacity of the car. Doors, the number of doors the car has. Weight, the weight of the car in kilograms. Now that we have an understanding of the data and its variables, we can proceed to explore and manipulate the data frame using Panda's powerful tools and functions. For example, we can calculate summary statistics, filter data based on certain conditions, handle missing values, and perform various data transformations and analyses. We have also seen that, when importing a CSV file into a Pandas data frame, there's an existing column that serves as the row index, so we can use the index_call parameter in pd.read_csv function to specify that column as the row index. This way, we don't need to keep the redundant unnamed 0 column. Here, we're using pd.read_csv, cars.csv, index_call equals 0, to read the file into a data frame called df. The index_call equals 0 argument tells Pandas to use the column at index 0, the first column, as the row index for the data frame. After executing this command, when you check the data frame, you should see that the row index is now the values from the unnamed 0 column, and that column itself is no longer present in the data frame. This is a useful technique when you have an existing column in your data that can serve as a unique identifier or row label. By specifying it as the index_call, you can get rid of the default numeric row index, 0, 1, 2, and use your desired column as the row index instead. If you mention that setting index_call equals 1 would make the price column the row index, which is not what you want since price is a feature column, not a unique identifier. Using an existing identifier column as the row index is generally a better practice than using a feature column for that purpose. Now let us move on to making a copy of your data, as there might be situations where we need to work with a copy of our data without modifying the original dataset. In such cases, we can create copies of the Pandas data frame. Python provides us with two ways to create copies. First is shallow copy and the second one is deep copy. Let's start with the shallow copy first. As the name suggests, a shallow copy creates a new variable that shares the reference of the original object. It will not create a completely new object in memory. To create a shallow copy of a data frame, we can use the copy method or simply assign the data frame to a new variable using the assignment operator. For example, since you have the data frame df, you can create a shallow copy using shallow_copy equals df.copy, deep equals false, or, you can simply do, shallow_copy equals df. Both of these methods create a shallow copy of the data frame and assign it to the new variable shallow_copy. Now, what does a shallow copy mean? Essentially, when you make a shallow copy, you're creating a new variable that points to the same memory location as the original object. It doesn't create a brand new object in memory. So, any changes you make to the shallow copy will also be reflected in the original object, and vice versa. This behavior can be useful when you're working with mutable objects and want the changes to be reflected in both the original and the copy. For instance, if you modify the shallow_copy data frame, the changes will also be visible in the original data frame. On the other hand, if you want to create a completely independent copy of the data frame, where changes made to the copy does not affect the original data, you'll need to create a deep copy. To create a deep copy, you use the same copy method, but you set the deep parameter to true. df2 equals df.copy, deep equals true. In a deep copy, a completely new object is created in memory, with no reference to the original object. Any changes you make to the deep copy will not affect the original data frame, and vice versa. They are independent objects in memory. So, if you modify the df2 data frame, the original data frame will remain untouched and vice versa. The choice between using a shallow copy or a deep copy depends on your requirements. If you want to make modifications and have those changes reflected in the original data frame, you should use a shallow copy. However, if you want to keep the original data frame intact and have any modifications apply only to the copy, without affecting the original data, you should use a deep copy. In our case we will be using deep copy as we do not want to change the original data. Now, we'll learn how to get basic information or attributes from our data. One of the things we can do is get the row labels or index from the data frame. The syntax to get the index is pretty straightforward. We use DataFrame.index. This method can be used on any DataFrame object. When you run this command, it will display the row labels of the data frame. Row labels are essentially the index values assigned to each row in the data frame. In the output you showed, the row labels range from 0 to 1435. This makes sense because Python indexing starts from 0, and the total number of rows in your data frame is 1436 starting from 0 to 1435, inclusive. So, by using DataFrame.index, we're able to retrieve the row labels or indices of our data frame. This can be useful for various operations, such as selecting specific rows or checking the range of indices in our data. It's kind of like asking, "Hey data frame, what are the names or numbers you're using to label each row?" And the data frame responds by showing us the list of row labels or indices. After getting the row labels or index, the next thing we can do is get the column names of our data frame. This is pretty easy, we just use the .columns attribute. When we run this, it will show us all the column names in our data frame as a list. So, we get an output object that contains the labels or names of all the columns, like price, age, km, fuel type, and so on. Getting the column names is useful because it gives us an overview of what variables or features are present in our data. We can easily see all the column headings at a glance. Next up, we can also find the total number of elements in our data frame using the .size attribute. This will give us the total element count, which is the number of rows multiplied by the number of columns. In our case, since there are 1436 rows and 10 columns, the output shows 14360, which is 1436 times 10. This size attribute gives us the overall size or length of our data frame. Another handy attribute is .shape, which gives us the dimensionality of the data frame. When you use .shape attribute, it outputs two values, the number of rows and the number of columns. In our example, the output is 1436, 10, which means there are 1436 rows and 10 columns in the data frame. Getting the shape is useful because it tells us the dimensions of our data at a glance. We can quickly see how many observations such as rows and how many variables such as columns we're dealing with. So, by using these simple attributes like .index, .columns, .size, and .shape, we can easily retrieve basic information about our data frame, such as the row labels, column names, total element count, and dimensions. This basic information is often necessary before we start any data manipulation or analysis. After getting the basic attributes like index, column names, size, and shape of our data frame, another useful piece of information we can retrieve is the memory usage of each column. This can be helpful in understanding the memory footprint of our data, especially when dealing with large datasets. To get the memory usage of each column in bytes, we use the .memory_usage attribute with our data frame. When we run this command, it will output the memory usage in bytes for each column in our data frame. In the output you showed, we can see that all the columns are using the same amount of memory, in bytes. This means that none of the columns is particularly memory intensive compared to the others, at least in this specific data frame. The output also shows the data type for each column, which can be useful information as well. Different data types can have different memory requirements, so knowing the data types can help us optimize memory usage if needed. Getting the memory usage information can be particularly helpful when working with large datasets, where memory management becomes crucial. If we notice that certain columns are consuming a lot of memory, we might want to consider optimizing those columns or even dropping them if they're not necessary for our analysis. Additionally, this information can aid in identifying potential issues or inefficiencies in our data structures, prompting us to explore alternative data types or storage formats that could reduce memory usage without compromising data integrity. Overall, the .memory_usage attribute provides valuable insights into the memory footprint of our data frame, allowing us to make informed decisions about memory management and potential optimizations, especially when dealing with large datasets or resource-constrained environments. Next, we can find out the number of axes or array dimensions in our data frame using the .ndim attribute. This attribute gives us information about the dimensionality of our data structure. When you run this command, it outputs the number of axes or dimensions present in the data frame. In our case, the output shows 2, which means that the data frame has 2 dimensions. These 2 dimensions correspond to the rows and columns in our tabular data structure. It's important to understand that a data frame is considered a 2-dimensional data structure, regardless of the number of columns it contains. The first dimension represents the rows, which are the individual observations or records in our data. The second dimension represents the columns, which are the different variables or features associated with each observation. Even though our data frame may have multiple columns, it doesn't mean that our data has more than 2 dimensions. The data frame itself is still considered 2-dimensional, with 1 dimension for the rows and another for the columns. The reason for this is that a 2-dimensional array, which is essentially what a data frame is, stores data in a format consisting of rows and columns. Each element in the array is accessed by specifying a row index and a column index, hence the 2 dimensions. This information can be useful when working with multidimensional data or when dealing with operations that require knowledge of the dimensionality of our data structure. Now we will look into indexing and selecting data in Pandas DataFrames. In Pandas, we can use the Python slicing operator, which is represented by square brackets, and the attribute or dot operator, represented by a period, for indexing and selecting data from our data frames. Indexing allows us to quickly and easily access specific rows, columns, or elements within our tabular data structure. It's a powerful way to subset or filter our data based on various criteria or conditions. For example, if we want to select a particular column from your data frame, we can simply use the dot operator followed by the column name, df2.price. This will return the entire price column as a Pandas series. Alternatively, we can use the slicing operator to select multiple columns by passing a list of column names inside the square brackets, like df2, price, age, km. This will return a new data frame containing only the price, age, and km columns. Indexing and selecting data using these operators is incredibly convenient and efficient, as it allows us to quickly subset or filter our data without having to write complex loops or conditional statements. By mastering these indexing techniques, we can easily explore, manipulate, and analyze our data in Pandas, making it a powerful tool for data analysis and processing. Let us now discuss about head function, which is a handy way to quickly view the first few rows of a data frame. The syntax is straightforward, dataframe.head, n, where n is the number of rows you want to display. In this example, we used df2.head, 6, which will display the first 6 rows, or 7 rows in total, including the header row, of the data frame. If you don't specify a value for n, the head function will display the first 5 rows by default. Viewing the first few rows using head function is particularly useful when you want to get a sense of the structure or schema of your data frame. It allows you to quickly see the column names and a sample of the data, which can be helpful for understanding the variables and their values. Additionally, we can also use tail function, which is similar to head function but returns the last n rows of the data frame instead of the first n rows. We use df2.tail, 5, which will show the last 5 rows of your data frame. Even if you don't specify a value for n, tail function will still display the last 5 rows by default. The tail function can be handy when you're working with large datasets and want to quickly verify the data after sorting or appending rows. It allows you to see the most recent entries in your data frame without having to scroll through the entire dataset. Finally, let's see how to get the scalar value, meaning single value, from DataFrame. This is typically done using the slicing operator square bracket or the attribute operator dot along with row and column labels or indices. For example, if you want to access the value in the first row and price column of the data frame, you can use df2.lock 0 price. Using the uses the row label and column name. Accessing scalar values is useful when you need to retrieve or manipulate specific data points within your data frame, rather than working with entire rows or columns. Overall, these indexing and selecting techniques provide powerful and efficient ways to explore, subset, and manipulate your data in Pandas, making it a versatile tool for data analysis and processing. The AT and IAT methods provide a fast and convenient way to retrieve a single scalar value from a data frame. These methods are particularly useful when you want to access a specific value based on its row and column labels or indices. Let's start with the AT method. As mentioned, it provides label-based scalar lookups, which means you can access a value by specifying the row and column labels. Here's an example. In this case, you're accessing the scalar value that corresponds to the fifth row, row label 5, and the fuel type column. The output you got was diesel, which makes sense based on the sample data we provided. The AT method is handy when you know the row and column labels, as it allows you to access the value directly without having to worry about the underlying row and column indices. On the other hand, the IAT method provides integer-based lookups, where you specify the row and column indices instead of labels. Let's look with following example. Here, we are accessing the scalar value at the sixth row, index 5, and seventh column, index 6. The output we got was 0, which corresponds to the value in that specific cell of the data frame. The IAT method can be useful when you're more comfortable working with the row and column indices, or when you're dealing with integer-based indexing rather than label-based indexing. Both AT and IAT are efficient ways to retrieve a single scalar value from a data frame, as they don't require you to select an entire row or column first. They allow you to directly access the desired value, which can be particularly useful when you're working with large datasets and want to avoid unnecessary computations or memory usage. The choice between AT and IAT depends on whether you're more familiar with the row and column labels or indices. If you know the labels, AT is a convenient option. If you're more comfortable with indices, IAT might be the way to go. Overall, these methods add to the powerful indexing and selection capabilities of Pandas, making it easier to work with specific data points within your data frame when needed. Now let us look into .lock operator to select entire rows or columns from our data frame based on their labels. This is a powerful indexing technique that allows us to subset our data in a more intuitive way. To use the .lock operator, we start with our data frame name, followed by .lock, and then we use the slicing operator to specify the row labels and column labels we want to select. Inside the slicing operator, we provide two arguments. The first argument is for specifying the row labels, and the second argument is for specifying the column labels. In this example, we used df2.lock, fuel type. The colon in the first argument means select all rows, and fuel type in the second argument specifies that we want to select the fuel type column. So, this code will give you all the rows from the fuel type column of the data frame. You can also select multiple columns using the .lock operator by passing a list of column labels as the second argument. The .lock operator is particularly useful when you want to select specific rows or columns based on their labels, rather than their integer positions or indices. It makes your code more readable and easier to understand, especially when working with datasets that have meaningful row and column labels. Overall, the .lock operator is a powerful tool for indexing and selecting data in Pandas data frames, allowing you to work with your data in a more intuitive and label-based manner, making your code more readable and maintainable. So, in this lecture, we explored the functionalities of the Pandas library. We have looked into importing data into Jupyter Notebook and then proceeded to understand how to create a copy of your original data frame. Following that, we examined how to extract essential attributes such as row labels and column labels from the dataset. Finally, we learned techniques for data selection and indexing using operators like IAT, AT, and .lock. In our next video, we will continue our discussion on Pandas DataFrame. Pandas is a powerful Python library used for data manipulation and analysis. It provides data structures like data frames and series, along with tools for reading and writing data in various formats, handling missing data, and performing operations like filtering, grouping, and merging datasets efficiently. We hope that you have found this course informative. Please hit the like button and subscribe to our channel for more informative Python for data science content. Your support means a lot and motivates us to create more educational resources for you. Stay tuned for the next lecture, where we'll continue our journey through Python's data science course. Thank you for watching and see you again.